So my name is Anastasios Kyrillidis. You can call me Tasos. I come from the computer science department. And my area of expertise is I like algorithms. So I like optimization. I like to design things to work efficiently. Either this means work clock time, whether it means like energy, whether it means like how much memory it needs, et cetera, et cetera. And given the lack of like a lot of time, I will try to give you like an overview about the topics that I'm actually working on right now. It's going to be glossing over like skimming over some topics, but I will focus on one thing that I feel like it relates also like to high performance computing. Okay, so one thing that I assume that everybody now knows and now people start believing is like the large language models actually rule. It's not that we understand why, but I will try to give you like a useful list of like what it entails so that we actually build this kind of like models. So what do I have here in this table, okay, is the following. You see here some names, some companies, and I'm going to explain some of these numbers. Okay, I think that this creates a problem here. So maybe I can actually keep it here. So these are the numbers that they define the billion of parameters that these models actually have. So you might have some models that they have like, let's say, 2 billion parameters to worry about and train. And of course, there are some question marks. This is where GPT-4 is assumed to be with 1 trillion of a parameter model. So this is a huge model, and it entails a lot of like time, a lot of like effort, and a lot of like HPC plus energy in order to make this actually happen. Okay, so just to give you an idea, if you're thinking as a company, as industry, as whatever like institute to use like a 7 billion model for whatever task you have, you need at least 24 gigabytes of RAM just to ask a question and get an answer. Okay, and if you want to train it, and I'm very optimistic, you need at least 56 gigabytes of RAM. And I'm saying optimistic because I really put all the numbers down so that it actually fits in a 56 gigabytes of memory. Okay, so it requires a lot of hardware, it requires a lot of energy. And of course, based on the task, based on the data set, this is going to take forever to train. For example, to give you an example, GPT-3 was a 175 billion model. An equivalent model of that, which is open source, is actually called the Bloom model. And I think it took around of 118 days of training and using I don't know how many really, I think it was more than 1 million GPU hours on really high-end NVIDIA GPU. So this is a lot of energy, okay? So we heavily rely on some hardware, which is actually NVIDIA. We heavily rely also on the software that comes with the hardware, which is a good thing. I mean, they give us the functionality, but at the same time, maybe you have a new way of training your model. You're actually restricted from that in the sense that you have to build your own kernel, your own software, et cetera, et cetera. Okay, so this is not an ideal scenario as a player like me. I'm at Rice University. It's not that I have like millions of dollars to build like and have like clusters. So I have to think out of the box to design new ways, maybe more efficient, in order to actually train this kind of like models. Okay. So now you can see like these are the players that they can actually train this kind of like models these days. So let me actually start with what is needed to train such models. Okay. By the way, this is not a talk about large language models, but that's the current state of the art right now. So you need a data set, right? So I assume you guys have your own data sets, and this is what I'm going to actually highlight here. You might have data sets that are actually only text here. Here I use the example of Bloomberg. They actually designed their own financial GPT model so that you can actually ask questions about finance, right? So you can actually build your own LLM based on your own data, okay? And these are text data, but maybe they can actually be visual data. What I would like to highlight here is that some of this data is actually open source, but some of it is actually your own, let's say, data, which I believe like it's your gold these days. That it's actually something that you should actually use and in order to train the model, and based on your own data internally in your company, maybe you can actually have a very nice, let's say, assistant to help you in your internal, let's say, tasks. Okay, so of course, data is not everything. If it is garbage in, garbage out, I have been hearing this since I was actually a PhD student. Okay, so you have to actually clean it, and you have to do some pre-processing. What I would like to highlight here is this is important because there is a trend from large language models to small language models, which is the idea that if your data is clean enough, here I use the word textbook type of data, which is clean enough as a textbook, might be enough so that you can actually decrease the size of the model and still have like very good results. Okay, so this is a trend very recently. Here you might see some models that they come from Microsoft, from Google. So even if you know, for example, Gemini, it's not like one version of Gemini, there are different versions of Gemini. So this is something that because of energy constraints, they really want to have like, not go in the direction of large models, but maybe in the direction of small models. Okay, so of course you have to choose the model size, okay? And there are some scaling laws, as they say, but many of them, they're actually under criticism because it all depends on your data. It's not like you know that you have 50 terabytes of data, it means that the size of the model should be that much. It also depends on the quality of the data, so this is actually kind of like unclear, okay? And of course, a lot of money, hyperparameter tuning, and you hope that this is going to run. Okay, that's kind of like the whole cycle of like training this kind of like models, and it has a bit of luck towards the end in order to make it work. Okay, so is this the end? Because if this is the list that you should actually actually follow, then maybe you can actually train whatever you want as long as you have the energy, the money, the power, et cetera, in order to do it. Okay. Hopefully, that's what I'm working on. It's not. Because of the reasons that these models are actually really big, we have to think about the algorithms underneath it. Of course, we have to think about many things. For example, is the hardware accelerator optimized in terms of like energy? Do we need all this data? Do we need the models to be that big? I think in terms of like algorithms. If I design a model, do I have to go over all the parameters at all times in order to optimize my model? These ideas are old. For example, they start from the idea of assume that you have a model. Maybe I don't like visit every parameter of the model when I train it every time. Maybe I can skip some of the parameters. Maybe I can decide on the fly, I'm already having an answer to my problem after 6 layers of my model. Even if my model is 24 layers, maybe I can actually early exit and give you an answer, right? And the most famous of that is what it is called the mixture of experts, which is the idea that the model itself has part of it where I can actually make selections which parameters are going to be activated based on the input, the question that I have. So if my question is very specific about the topic, maybe cleverly the system will decide which of the parameters are going to be activated on the fly so that I don't have to go over all the parameters at the same time. Okay, and of course this is not a complete list. This is the algorithmic side. By the way, these decisions that we make, they change the way we train the model. It's not a regular gradient descent where I take all the parameters and I train everything at the same time. It's more like I change the functionality of gradient descent. Now, this is not only on the algorithmic side. There is also ideas from the HPC, which is distributed computing side, where the idea here, for example, is like classically we thought, we have a lot of data, let's spread out the data over over the compute nodes that we have. Now we talk about other kind of like things. Instead of only the data, we also split the model. And this is the way that these models are actually trained. Like we couldn't have like GPT-4 unless you actually decide how to split the data, split the model in order to achieve like and make it actually run. Okay. Again, not a complete list. So what is this talk about? That's my lab's vision. That I would like to tell you is like, imagine that you have like a big model. And I really believe that it is possible to train the big model by training smaller versions of the same model. Okay, how you define a smaller version, that's kind of like many topics that I could actually discuss today, but I'm going to only discuss one approach. Okay, but that's the main idea. And this idea actually, even it doesn't have to be AI and machine learning. It's more about any optimization problem that you think of. Is it possible to train a big model as an AX equals B linear system of equations by solving smaller system of equations in parallel and combining the solutions as we go? Okay. So the idea is like based on the task that you come in, that comes in, you decide on the fly how you're going to train the model, whether it's going to be the full model or part of the model, and how you're going to adapt to that. Okay, it's not a thing, I just made it up. Don't try to think what is just in task like it doesn't exist. Okay, so just to give you an idea, I will skim over the three approaches and I'm going to focus only on one of them. Okay, so the first approach is as follows. Here what you see is like you have an input, is your data. You're going to have an output, which is the answer. And in the middle is going to be a model. Okay. The first idea is the idea that instead, as I said, instead of having a big model, is there a way that I can actually split the model into smaller versions of that? And I'm going to explain it more. And in a way that it is random enough that it will help you this randomness. And you repetitively do that. So you have the big model, you split it once, you train all the smaller models in parallel, you get all the information together, you split again, you get it together, split again, and you keep doing that. And it turns out, and I'm going to discuss how this relates to HPC, it leads to lower communication among the workers, lower computation per worker, without losing much. So somehow, naively using gradient descent might not be the best way to do it. Of course, this is not like it works always the best, but definitely it saves you a lot of communication and computation time. Okay, that's the idea of like having a big model and how I can actually train a big model. The other approach is the idea like, why do I care about the big model? Maybe I can actually have many small models independent, and cleverly I can select which one I'm going to use based on the task. That's the idea of mixture of experts. Okay, that it's actually quite used. So imagine that you have like, I need to do a computer vision task, but the computer vision task is actually split into like edge detection, object detection, et cetera, et cetera. So I'm going to call 3 different agents in sequence in order to solve my problem. Okay. And what it is now, and I'm not going to talk about this, is it's the collection of these 2 things. This is where we are right now. Like, we have big models, but we want to adapt to new tasks. So the way to do it is like, I'm going to use the backbone of the big model, and I'm going to slightly change something at the very end or in parts of the model so that I can actually adapt to new tasks. This is what it is called PEFT. You might have seen it, or you might seen it, is the parameter efficient fine-tuning, which is the idea that I have the big model, I download the pre-trained model online, and then I have to adapt it a little bit because I'm a different company with different data so that I can actually make it work for my case. Okay. And in this case, also, we have some scenarios and results, but I'm not going to talk about this. So what I would like to talk about is the first approach. Assume that you want to train a big model, right? So here, in the middle, you have a large model. Think of like from 2 billion to 175 billion model. Okay, in order to train these, as I said, you need a lot of GPUs, you need to communicate a lot among the GPUs, you need to spend time, energy, so it is quite like not very much efficient. Okay, so the idea that we propose is like, first of all, we have to figure out a way to split the model into a more meaningful, let's say meaningful but smaller models of the same type. Think of it like a system like this has a number of layers. Every layer has some parameters there. Maybe I can sub-select some of the parameters per layer such that I actually create smaller versions, let's say more narrow, but there are many versions of that in parallel, and I actually treat them as smaller versions of the big model. Okay, now what I'm going to do, after I do this once, I train this distributedly, and then I tell them, don't do it forever. Give me your update. I will recreate the big model before I split it again into new models, which are not the same as before. Maybe I randomly pick things that were actually included in a different model, submodel in the previous iteration. Okay. So the idea, this is a distributed protocol. It actually says the following: assume that your model is super big. It will never be sent to all the workers in a distributed fashion as a whole. It's going to say that if I have 175 billion, I don't have to send 175 billion to every worker. I'm going to send a smaller version of that to every worker. So I save communication. Now, per worker, I don't have to do gradient descent on a big model. I'm going to do gradient descent on a smaller model. And then I will get back the results before I recreate actually the big model and keep doing that again. So it saves communication, it saves computation, and it turns out that it works really well. Like, it's not like something that you will get like really diverging and it will not make any sense. Okay, so just to give you an idea, I think it is best described with a simple example. Okay, I know this is not large language model, but I cannot explain it as a large language model in an audience really well unless it is a simple model. So what you see on your left here is like a very simple neural network. It is in a bottom-up, let's say, representation where you have your input, some hidden layers, and then you have the output. So what are the parameters here is every edge that you see in this picture. It's actually the weights of the neural network. Okay, if it was a classical distributed framework, you could actually say, this is the current version of my model. Assume that you are the workers. I have to send this model to every one of you. So the communication will be to everybody. You get this model, then you have your own local data. You train this a little bit, and then you say, Tasos, I'm ready. Are you ready to get my update? Then you send me everything that you have from all of you, which means that I have to send these to, I don't know how many participants we have right now. Then you have to deal with this big of a model, and then I have to get all the updates from you, and then I have to repeat that many times. What I'm proposing is the following. Instead of sending the big model, can I send this small model to Samantha, the other small model to Angela, the other small model to whatever else, whoever else, and I keep doing that so that you guys have to see a smaller model instead of the big one, and you train a smaller model on your local data. So I saved communication, and locally you save energy because you don't have to deal with a big model. Then whenever you're ready, you tell me, I'm done, a little bit like I ran 10 iterations. Do you want my updates? I will get your updates, get this back, and then whenever I communicate to you again, I will never send to Samantha the same network. I'm going to subsample and maybe send a neuron that it was actually in Angela's case in the previous. So there is implicitly sharing information as it goes. Okay, so it's not like I send the same model to the same worker all the time, because then it is mixture of experts. It's like independent models, and it has nothing to do as a big model. Okay, so this actually created, and probably you don't care about this, this is an idea that dates back in 2019, and we made it work for several neural networks. It's not the same idea easily applicable to everything, because every neural network has a different structure. So we have ideas that actually apply for simple, like the first idea was just like feed-forward neural networks. They are useless, but it is the basis. If it doesn't work there, it will never work to anything else. We managed to have it like on residual networks, which is more like computer vision, or convolutional networks, or graph neural networks. Okay, so transformers are not there because these are actually being done right now. And we're trying to figure out what is the component, what are the components in a transformer model, in a GPT model, that we can actually split it so that we don't lose much in terms of like accuracy. So how would that work again? As I told you, this is the model. The model is actually sent to a parameter server. I'm the parameter server. I'm going to send you not the full model, but actually indices of the full model to each one of you. You actually train it. This is what you see as a worker. You actually train it locally only, okay, for a couple of iterations before, this is one iteration before the next iteration starts, okay? So how does it work in practice? We managed to handle cases that were not actually possible before faster, okay? We managed to actually really see linear scaling in distributed computing, of course, small scenarios, but we didn't have like the hardware to see if I have like 100 GPUs, do I still see a linear scaling 100 times faster? So far, 4 or 8 GPUs, we can see 4 times, like we have linear scaling, and for 8 GPUs, we see 6 times. So we do not really get 8 times, let's say, acceleration. It works probably, I'm not sure how many of you know federated learning as a scenario. It is the case where maybe there are some entities like we have here, Cell, Chevron, et cetera, they don't want to share their own data, but still they want to collaborate in order to solve the problem. In this case, this is the federated learning scenario where they say, let's train a model together privately. We're not going to understand each other's data, but we would like to solve the same problem. And in this case, this is the scenario we talked about. Would you keep your own data? We'll just send you a model. You train locally and you send the model back. And there are privacy-preserving mechanisms so that I don't understand your data, but that you just give me some numbers that I can actually use in order to train, to keep training the model. So we figure out that what we had in mind, not in terms of like Chevron and BP and so on, but mobile phones. Your mobile phones in Google are part of a federated learning scenario. Like the fact that your mobile phone knows your next word when you write like a text is because they know you locally as a personality, but at the same time they send your data privately to learn a bigger model in a federated sense so that this actually keeps improving, okay? So it turns out that this kind of like idea of less communication and less computation works really well compared to the state of the art, while the communication is lower, this is the gigabytes, compared to the state of the art, and at the same time without paying too much like of gigaflops in order to actually solve the problem, okay? So the last thing I want to say here, we managed to train like a graph neural network, which is the wider ever that we know. Like it is a neural network for graphs, where the width of the neural network is at the level of 32K, let's say, parameters, which is big enough to actually, we don't know any work that actually handles that many of like per layer width of a graph neural network. So before we close, I just want to say that I will have these cards available to everybody about approach number 1, but also the other 2 approaches that I didn't describe, which is the mixture of experts and the mixture of, let's say, parameter efficient tuning, because I think they're under the same story. And the story here is like, do we necessarily have to consider the models as a single monolithic model? Or should we actually start thinking everybody's going to have a collection of models that they actually train, and maybe they can combine these models together in order to solve different tasks? For example, here, as I saw, maybe task 4 is nothing else but taking task 1 and task 2, add them together, and let's say you subtract task 3 and then you get actually task 4. I don't have to train a new model in order to get task 4. Maybe I can combine the knowledge that I have already, and that's the idea of the taskonomy, that maybe all the tasks that we want to solve, they're actually sorted in a way and connected so that you can actually solve more complicated stuff by combining things that you already know. Okay, so just to close this talk, I just want to say the following. I like adversities because they create opportunities. I don't have like hundreds of GPUs to just use gradient descent and so like get a model. So I need to think out of the box how I can actually do that because I have limited hardware. And I just feel like we need new protocols in high-performance computing and distributed computing, and I think that we can actually, that's kind of like an interaction we need. And yeah, there are tons of open questions that we still want to solve, and hopefully new applications from industry, for example. It's something that can actually lead to different solutions. But yeah, that's it. Thank you very much, and I hope you have a great day. Any questions? Yeah.
Hey, Tasos, really interesting talk, really great stuff. Thank you. This wasn't exactly your topic, but since we're talking about splitting models, you mentioned the concept of federated learning.
Yeah.
I don't know if you're familiar with, Dan Stanzione mentioned it yesterday, but this like exploit around somebody prompting an LLM with company, and then it spit out a bunch of stuff that wasn't stored as strings in the model. Is that curious if federated learning would have a similar exploit and need to be de-risked for folks in this room?
Definitely. I think that all these models, I'm not sure whether the big models are trained with the privacy preserving mechanism. In federated learning scenarios, they really they make the whole training process slower by adding noise that actually guarantees the privacy, which actually makes their application not as fancy as the ones that you talk about, because if we add privacy at this level to the large language model, it will take forever for them to train. But I agree with you, that's an issue, but that's the thing, that's why there is a trend. Do we need the large language model? Can we actually have a smaller language model? And if, for example, your company comes with their own data, do I need 100 billion parameters? Maybe I just need 1 billion for the task that I want. And then if you want to be private, then in that case, you can actually add the privacy that you need. But yeah, that's a concern.
So I don't want to eat too much time, but you said there's data, like fuzz data that's put in there to obfuscate it. Is that kind of where the privacy comes from?
It's not that it is data. It's more that while, for example, your gradient is accurately computed, your gradient, even if it is not access to your real data, you can reverse engineer from the gradient on which data it actually was trained. So by adding noise on purpose, you're actually making fuzzy what is the gradient information so that nobody can actually get the information you want, which is exactly what you actually said. Yeah. Thank you.
Right.
Yes.
So kind of key to this technique is to be able to split the models. But I'm unclear how you actually do those splits.
That's a great question. That's why if it was the single split, I wouldn't have 4 papers, each paper for each, let's say, model. So I'm just saying that it is possible. I'm just saying that now that we're getting into transformers, which is the large language model, is everywhere, whether it is text, whether it is image, whether it is all these things, it's going to be the same architecture. That's why now we're focusing on this model, and if we figure out a way which is kindly automatic to do that, then we're done. I know it is we started with a simple model, but then we said that, okay, this is simple, let's go to convolutions. Oh, that's quite different, we have to do other things. Let's move to ResNets, other things. Now we get into transformers that it has been consistent now 6 years. It is consistent that this is a quite expressive model to solve many tasks, which means that maybe now we should focus on this, and if we figure it out automatically, then we're done. Yeah. That's the idea. Okay. Yeah. Good question. Thanks. Thank you.
This is just a comment. This directly hit me because brilliant idea. Because in seismic data processing, we do the similar thing. We do individual shot processing, and once the image is created, we do the stacking towards the end, and everybody gets a fresh model and all those things, right? So
yeah,
amazing. Thank you.
No more questions. Thank you.
Thank you very much, guys.